So we've already talked about the relationship between the angles created by transversals and parallel lines when we already know that the lines are parallel. Now in this section and in this video, we're going to turn that completely around and talk about what kind of evidence can we use to show that lines themselves are parallel when they're cut by a transversal. Because obviously we can't go infinitely in both directions down the lines and check to make sure that they never intersect. If they're on a coordinate plane, then as part of an algebra class, you've already talked about what parallel and perpendicular slopes look like, so you can check their perpendicular slopes. But on a plane that doesn't have any coordinates on it, we can't check that either, so we need to have some other sort of information. And as it turns out, those same two postulates and theorems that we started with last time, the corresponding angles postulate and the alternate interior angles theorem, are things that we can use to say not only that angles are congruent if the lines are parallel, but we can use information about corresponding angles and alternate interior angles to say whether lines are parallel at all. So if we go back to that familiar setup that we had, where we had two lines, L and M, that were cut by a transversal K to create all of these different angles that we could talk about as alternate interior angles, corresponding angles, etc. What we saw in the last video was that if two parallel lines are cut by a transversal, then corresponding angles are congruent. So if L and M were parallel, we would know that 1 and 5 were congruent, 2 and 6 were congruent, etc. Well, if we take the converse of the corresponding angles postulate, switching the if and then statements, we get something that reads like this. If two lines are cut by a transversal so that corresponding angles are congruent, then the lines are parallel. And what that would allow us to do and allow us to say is that if, for example, angle 1 were congruent to angle 5, that would tell us that L is parallel to M. And much like we took the corresponding angles postulate in saying that parallel lines mean congruent corresponding angles without proof and use it as a postulate, we're going to do the same thing here. Because if two lines are cut by a transversal so that corresponding angles are congruent, then the lines are parallel is the converse of the corresponding angles postulate, and we're going to accept that without proof, that it is true. So go ahead, pause the video, copy down the converse of the corresponding angles postulate, come back when you're ready to move on. So this is one piece of evidence that we can use to show that these two lines are parallel. For example, if we knew that angle 2 and angle 6 both had a measure of 135 degrees, that would be enough to tell us that L is parallel to M. And it's important when you're doing problems like this to pay close attention to which lines we can say are parallel. Because if we have several lines with several transversals, it is really easy to get confused about which lines are the parallel lines that we're trying to prove and which lines are the transversals. Now, also in the last video, we took the idea of corresponding angles and we extended it to find the alternate interior angles theorem. And in this video, we're going to do the same thing with the converse of the alternate interior angles theorem. That is, if two lines are cut by a transversal so that alternate interior angles are congruent, that is, if angle 2 is congruent to angle 3, then we know that the lines themselves are parallel, that L is parallel to M. So go ahead, pause the video, copy down the converse of the alternate interior angles theorem, as well as the diagram here, come back when you're ready to see an example problem, and move on. We are not actually going to go through the proof of the converse of the alternate interior angles theorem as a part of this video. That is going to be the first proof that you do as part of a practice with proofs problem set involving proving that lines are parallel. But the strategy for it is going to be very similar to what we saw in the last video, using corresponding angles, conveniently, 1 and 2 here, to prove the alternate interior angles theorem. Instead, what we're going to do is we are going to do one practice problem to take a look at what we can do if we know that we want to use this to create parallel lines. Over on the right-hand side, just like the last video, we have the converse of the corresponding angles and alternate interior angles postulates and theorems. And what we want to do is we want to find a value for x so that lines L and M are parallel. Go ahead and pause the video, see what your intuition says about how we would solve something like this. Come back when you're ready to see the process and then wrap up. So if we want these two lines to be parallel, that means we want the alternate interior angles to be congruent. And if we want the alternate interior angles to be congruent, that means that the two values, 5x plus 7 and 7x minus 21, will have to be equal, then the angles are congruent, and if the angles are congruent, then the lines are parallel. Well, here this is a relatively straightforward linear equation to solve. Add 21 to both sides to get 28 on the left side, subtract 5x from both sides to get 2x, and end up with x equals 14. So for the value of x equals 14, L and M are parallel, and for any other value of x, 5x plus 7 is not going to be equal to 7x minus 21, so the lines themselves would not be parallel. So again, if you want to prove that lines are parallel, the first two places that we can start are with the converse of the corresponding angles postulate, that is, corresponding angles being congruent mean that lines are parallel, and the converse of the alternate interior angles theorem, that is, congruent alternate interior angles tell us that the lines themselves are parallel.